Hello there. In this video, we're going to discuss how to deal with probability density functions of several variables. In particular, we're going to be focusing on the two variable case, namely joint probability density functions of two variables. If you have three or more variables, the process is going to be similar. So the density function or the function that we're going to be focusing on, we don't necessarily know if it's a density function or not, is going to be the function c times x squared plus y squared, such that all points x and y are going to be located in the unit cube. So the Cartesian product of 0, 1, and 0, 1, and it's going to be defined to be 0 otherwise. So in this video, we'll introduce how to sort of deal with probability density functions of two variables, and also in the next video, we'll talk about how to calculate the mean and variance of these types of distributions as well. Alright, so let's begin by talking about the properties that a function must have that is multivariable in order for it to be a probability density function. So f is a probability density function if two properties satisfy. So these two properties is going to carry over from the single variable probability density function. Namely, fxy must be greater than or equal to 0 for all pairs of points xy in the support of your function. And moreover, so we're going to call the support S. And secondly, the double integral over the region S of fxy dx dy must be equal to 1. So these properties definitely do share some patterns to the single variable case. So for our function that we have, let's see what value of c makes this a probability density function. So let's do some practice on double integration. Alright, so what we want is that the integral from 0 to 1 of cx squared plus y squared dx dy, what we want is this to be equal to 1. Alright, so let's focus on the integral on the inside. So let's partially integrate with respect to x. So we're going to treat y as a constant. So this is going to be equal to the integral from 0 to 1. Let's pull out our c actually before we get into the integration part. So this is going to be equal to c times the integral from 0 to 1, integral from 0 to 1. So this is the y integral, this is the x integral of x squared plus y squared dx dy. Alright, so let's partially integrate by x. So this is going to be equal to c times the integral, the y integral from 0 to 1. Integrating with respect to x, that's going to be equal to 1/3 x cubed plus, so y squared is going to be a constant here, so that's going to be xy squared, evaluated as x goes to 1 and as x goes to 0, dy. So using the fundamental theorem of calculus, what do we have? So when we plug in 1, so x cubed is going to go to 1, y squared is going to go to 1, so that's going to leave us with 1/3 plus, so x is going to go to 1, so y squared. When x goes to 0, both terms go to 0, so we can just ignore that term. So now let's integrate with respect to y. So this is going to be equal to c times, so that's going to be 1/3 y plus 1/3 y cubed, evaluated as y goes to 1 and as y goes to 0. So as y goes to 1, this is going to be equal to c times 1/3 plus, so 1 times 1/3 is again 1/3. And as y goes to 0, nothing happens since both terms have y in it. So this is going to be equal to, so 1/3 plus 1/3 is going to be 2/3 c. And we want this value to be equal to 1. So if 2/3 c is going to be equal to 1, then we have that c is equal to 3/2. So if that is the case, that means 3/2. That means fxy is equal to 3/2 x squared plus y squared, where xy belongs to our domain and 0 otherwise, is a probability density function. Alright, so once we have that, now we can start talking about some other things. So sometimes working with two-dimensional functions definitely can be a little bit more difficult. So that's why we introduce marginal density functions. So we look at just the x variable, so we sum up the x variable over the y possible values, and similar for the y. So similar for the probability mass function of two variables, we're going to have the marginal density function for f for variable x is going to be equal to the integral over the support of y of f of x y dy, and the marginal density function for a random variable y of value y is going to be equal to the integral over the support of x of fxy dx. So we're going to be looking at the same exact function as we had before. So the marginal density function for x is going to be equal to the integral from 0 to 1. So this is going to be a y integral. So this is y is equal to 0 and y is equal to 1 of 3 halves x squared plus y squared with respect to y. So since we're only integrating with respect to y, we're going to have x left in it. So of course it's a function of x. So fx of x is going to be equal to, so we can pull out our 3 halves, integral from 0 to 1 of x squared plus y squared dy. So, and you can write it as a partial y to sort of emphasize that x is a constant here. So this is going to be equal to 3 halves, so that's going to be x squared y plus 1/3 y cubed, evaluated as y goes to 1, as y goes to 0. So as y goes to 1, that's going to be equal to x squared plus 1/3. So this is fx of x. And we can make this simple and distribute our 3 halves. So we have finally the marginal density function for a random variable x is going to be equal to 3 halves x squared plus 1/2. Now notice that this function is symmetric in terms of x and y. So the marginal function for variable x is going to be pretty much the same thing as the marginal function for variable y, and you can verify that. So similarly, fy of y is going to be equal to 3 halves y squared plus 1/2. So it's the same function, just in a different direction. And you can verify the calculus out if you want. So how can you calculate probabilities with multivariables? So let's assume we're interested in finding the probability that x is less than 1/3 and x is greater than 1/4. All right, so our probability, which I'm going to call star, so star is going to be equal to, so we'll do a double integral of our density function, so 3 halves x squared plus y squared. Typically we do dx first and then dy, so our second integral here is going to be x. So since we want values from 0 to, what is that, 1/3? Let's make that 1/2, just to make things a little bit more nicer. Alright, so this is 1/2, so this is going to be equal to the integral from 0 to 1/2. In general, it's negative infinity to 1/2, but our support starts at the origin, so that's 0 to 1/2. And x is greater than 1/4, so remember our support ends at 1, so it's going to be 1/4 to 1. So remember to keep your integrals straight, make sure this is x and this is y. Same order. Alright, so now let's do our integration. So let's pull out our 3 halves, just to make things a little bit more cleaner for us. You don't have to if you don't want to. So we have the integral from 1/4 to 1 of the integral from 0 to 1/2 of x squared plus y squared dx dy. So we're going to be focusing on x first, so y is going to be remained as a constant. So 3 halves times the integral from 1/4 to 1. So y is a constant, so that's going to give us 1/3 x cubed plus constant. So integral of a constant is a linear function, so that's going to be xy squared. And we're going to send x to 1/2 and then x to 0. And then we're going to integrate with respect to y once we figure out what that function is. So this is going to give us what? So that's going to give us the integral from 1/4 to 1. So when we plug in 1/2, that's going to be 1/2 cubed, which is 1/8. And 1/8 times 1/3 is going to be 1/24. plus then 1/2 times y squared is just 1/2 of y squared. And when we plug in 0 for x, both terms have x in it, so they disappear. So then we're going to integrate with respect to y from there. So the integral with respect to y, that's nothing fancy. So that's going to give us 1 over 24y. So we're going to increase the power by 1, so that's 3. So we're going to get 1/6 y cubed, evaluated as y goes to 1 and as y goes to 1/4. Now both terms have y and neither of these limits are 0, so we're going to have some fraction action to deal with. So we're going to have 1/24 plus 1/6. So that's what you get when you plug in 1, minus what you get when you plug in 1/4. So we have 1/24 times 1/4 plus 1/6 times 1/4 cubed is going to be 1/64. So that's a journey for which you may give your younger siblings or whoever if they're learned fractions. So once you do all that fun math, you should get 25/128ths, which will product out to 75 over 256, which is approximately equal to 0.293, or 29.3% chance of that particular event occurring. So that's pretty much how you calculate the marginal density functions for variables of a multivariable density function, and also how you can calculate some basic probabilities associated to density functions of multivariables as well. Hope you enjoyed.